I'd like to remind you that we have 2 more technical talks, and then we have a talk from one of our sponsors right after in this room. And with this, when does concurrency matter?
Yep. Cool. Hey, I'm Cheeseman, and I'm going to talk to you today about behavior-oriented concurrency. This is a joint work between Imperial College, Uppsala University, and Microsoft Research. But before I get into the what of BOC, let's get into the why of BOC. So central to concurrency are 2 mechanisms: parallelism and coordination. Parallelism is executing tasks at the same time, so you can think threads, tasks, coroutines. And coordination is restricting access to data for an unforeseeable schedule. We believe there's an interdependence of the 2 mechanisms that should be recognized and controlled through a single powerful primitive. But why? Well, if you're building an async runtime, then relying on synchronization primitives can block your threads and you may screw up your runtime. On the other hand, if you're increasing threads to improve performance, you may harm scalability as threads start to race for resources. We're certainly not the first to recognize this. Primitives should exist. An early advocate for this was actors. But actors have a serious pain point, which we aim to address. So what do we want? We want isolation. Behaviors execute as if no other behavior is executing at the same time. You want parallelism. The behaviors that don't have dependencies on one another can execute at the same time. You want ordering. That the programmer's written order of their program influences the order in which behaviors are executed. And you want deadlock freedom. But actors have all that, but actors really struggle at one thing: when you have atomic operations over multiple actors. So consider the transfer here. You have 2 accounts represented by actors, and you're trying to transfer money from the source into the dest. An actor can only influence its own state, so how do you influence 2 states at one time and don't see a partial transaction? I'm going to show you how we do it. Oh, sorry. On top of that, if you want to order multiple atomic operations, it becomes way worse. So here we're doing the transfer. We have 4 actors: the teller, the source, the dest, and the manager. The teller tells the source it wants to acquire it. The source says it's acquired. It tells the teller it's been acquired. The teller repeats that with dest. The teller sends a debit and a credit message to each of the actors, telling the manager that's going to coordinate the transfer. Those 2 actors tell it it's now going to stash and it's not going to enter any other transaction. The teller can now release those and start so they can take more messages. The 2 actors tell the manager that they can do the transaction. There is enough funds. They are not in any other transaction. The manager tells it to commit, and that those updates should become permanent and complete. That's a lot of messages. You build your own synchronization mechanism on top of a concurrency paradigm. So what's the box solution? It's that simple. You just do a when on the source and the dest, and then you can access and update them atomically. That's amazing, right? But I didn't explain what any of that meant. So in a nutshell, BOC is composed of 3 things. You have cones, or concurrent owners, and these are protect pieces of separated data. It's a single entry point into them. You have behaviors, which are units of concurrent execution. They modify your cones. And you have when, which is the single powerful primitive, which ties the 2 together. You spawn a behavior with a set of required cones, and then you can modify those cones. So you can think of cones and behaviors as resources and tasks, or locks and lock guards, whatever sort of makes sense for you, but the whole thing for us is BOC. So coming back to these points of what do we want for a concurrency mechanism, let's look at this example. We have a behavior which executes on source and dest and source dest, and we have some logging in between. So there's clearly some intention here with the program. When we say we want isolation, we want credit and transfer not to happen at the same time. They both use the source cone. When we want parallelism, credit and freeze don't affect the same cone, they can execute at the same time. We want ordering, that credit uses the source cone and so does transfer, so one should come before the other because the program has written down this way. But here we actually want a deeper notion of ordering. So credit came before transfer, so we want the logging of the credit to come before the logging of the transfer. We want deadlock freedom, and I'm going to add one more property here. We want flexible coordination. We want to fix the multi-actor update problem, and this is the bit on line 9. So how do we get that with BOC? To answer that, I'm going to walk through an abstract execution of a BOC program and show that we get all that. So on the left here, we have the program that we're currently executing, and on the right, we're going to start building up a DAG of behaviors. So here, we spawn the credit behavior. It gets into the DAG. It's pending, so it's red. We now spawn the freeze behavior. There's no dependency between credit and freeze, so there's no edge in the DAG. We spawn the transfer, and so here we have the flexible coordination. We're spawning over the 2 cones, and we can enter the DAG. We have ordering. The credit uses the same cone as the transfer. The freeze uses the same cone as the transfer. We're going to execute this DAG from top to bottom, so we're going to get that credit and freeze happen before transfer. And we have deadlock freedom. We're building a DAG of operations, so we can't enter a cycle that ends us in no progress. So we start executing the program. We execute the credit behavior, and we can also execute the freeze behavior. So we have parallelism. Behaviors with no dependencies can execute at the same time. Okay, we terminate the credit and the freeze, and we start executing transfer and the log C. So we have isolation. The transfer used the same cone as the credit, so we couldn't run them at the same time. It's one then the other. And also, we have this deeper ordering that I mentioned earlier. So you see that because credit came before transfer, we get that the log comes before the log T. So log C and log F will come before log T. So coming back to those properties that we wanted, we have isolation, we have parallelism, we have ordering, we have deadlock freedom, and we have flexible coordination. So we got all the things that we asked for. But how can you use that? So we have developed a formal concurrent semantics. This is the semantics. This is all the semantics. It's truly just these 4 rules. It's very succinct. And we make it this succinct by building on top of an abstract underlying programming language. We don't add when to a simply typed lambda calculus, and by doing this, we can then let any other language that fulfills the properties of that underlying language adopt BOC. Coming back to how can you use it, we've also built a C# implementation, which backs onto a C++ runtime, which can act as the library for other languages. So let's look at that C++ runtime. So we've added that flexibility. We've got something great. Has there been a cost? Did we screw it all up? How do we measure that? Well, does BOC work in practice? Does it pay this horrible cost? And does BOC address the multiple actor update problem? So, to answer that first question, we built Savina, the actor model benchmark suite, in BOC, and we compared it against Savina in Pony. So we've done this for 2 reasons. Pony's been shown to be as good as other actor languages or best in the Savina benchmark suite. So if we compare against Pony, we feel it's reasonable to say that we're comparable to the rest of the actor model languages. We do it against actors because there's a very trivial transformation from actors into BOC. And so if we don't have an overhead there, we think it's fair to say there's no overhead introduced. So in this graph here, there's the benchmarks in the leftmost column, and then green means there's more than a 20% speed up from when we build it in BOC. The squiggles is we're roughly the same, and the red plus is there's a bit of a slowdown in BOC. And as you can see, tons of green. So we think it's fair to say the flexible coordination came without an added overhead. To demonstrate that the flexible coordination scales, we took one of those Savina benchmark suites, the banking example, and we changed it in the way that I showed you before. We removed all the communication overhead that had to exist in the actor model and just did the when over the multiple cones whenever we needed to. And we can see that when there's substantial amounts of work to be done, as we scale the hardware threads, we see this nice curve coming down. So we feel that the flexible coordination scales. So coming back to those things I asked about evaluating, we think it works in practice. You don't have a horrible overhead, and it answers the multiple actor update problem. It scales nicely. So I hope I've sparked an interest in behavior-oriented concurrency, and I know you're going to go and read the paper, so what can you find when you go and read it? There's a lot more. There's a high-level description of BOC. We walk through the features of BOC by example, introducing it slowly. We build that semantic model that I showed you just before, and we talk about the properties that are required of an underlying language and how you get certain guarantees. There's more details of the C++ implementation, how we build that DAG, how we ensure that the runtime doesn't introduce deadlock, and a lot more. And there's a thorough investigation of the evaluation that's shown just now, plus a few more details. So examples of why sometimes we're worse than Pony, why we improve other ways. So, in conclusion, we think that when is a simple, intuitive, and expressive mechanism. It provides a single mechanism for both parallelism and coordination. It addresses the multiple actor update problem and performs comparably with existing actor languages. Now, this work is much more than just my own. It's been the collaboration between all these people who work at Imperial and Microsoft and Uppsala. And BOC is more than just an independent project. It's part of Project Verona, which is a programming language aimed at building cloud infrastructure. So another part of that is Reggio, a talk which was presented earlier by Ellen, which builds the language that serves as the underlying language to BOC. So I'm going to leave you there. I hope you've enjoyed the talk, and I'll take questions. And I'm graduating early next year and would love jobs.
Hello. So in the, let's say, core slide, when you show that you use your when between two actors instead of the manual coordination, how that work? Like, is it something like, is the semantic like, I am sending a message to both actors, and so a single thread of execution is...
So you're thinking of it like actors, right? So actors have message queues. In behavior-oriented concurrency, we separate the message queue and we separate the behavior and the state. So you don't send a message to the code. You sort of create, as I said, the DAG. And once you've built that DAG, you can just execute because you know that there's no race.
Okay.
You sound unconvinced.
No, I understand. You can also visualize it as one actor sending its data to the other actor and then having the data back or something like that?
But that would come with a runtime overhead.
Sure.
Yep.
So this might be related, but it might also be an earlier question. I'm a little bit confused about why you posed this in the framework of actors at all, because I don't see any actors in your solution. It just looks like concurrent imperative code.
Interesting. Yeah.
Okay, so can you resolve my confusion?
Of how it's like actors, how it's unlike actors, or both?
Yes, I mean, maybe it isn't, but I assume it is because you presented it that way.
Yeah.
It's similar for me.
So in the way of actors, it's all asynchronous spawning behaviors that execute all over the place, right? So when you take that, like behaviors are, it looks like imperative code, but it's not blocking in place. Every spawn is an asynchronous behavior that will execute asynchronously. So you're not like walking through the behaviors one by one, like typical imperative. It's not like locks and lock guards, if that makes sense. That's where it moves away from being that kind of imperative code. Does that make sense?
You're certainly blocking until you get the resources for a when, right?
No. So sorry. When you do a when, you just spawn, you put them in the work queue, and you move on straight away. You don't block in place.
Okay, so if there's something afterwards, it can continue even when that when is waiting.
Yeah.
Interesting. Okay, thank you.
Over here.
Hello.
Can you say something about what went wrong with Civ?
What went wrong with SIFT?
You had the Civ, the benchmark that had two red blobs next to it.
We can't see your slides anymore.
Sorry.
Yeah.
What went wrong with Civ? What went wrong with it? Normally, it's one of two things. It's that Pony is a much more mature runtime, and so it does things like backpropagation, which stops you.
It was the generation of the development division instruction.
Yes. Okay, this was ridiculous. Pony, for some reason, generated it in 32 division, and we didn't, and that was the whole difference. If you just manually change the binary to do it in 32 division, it fixed the whole benchmark.
Let's thank the speaker again.